Hello everyone, I hope you guys are doing extremely well. Today we are going to discuss the first problem in our binary search tree series. The problem name is insertion in a binary search tree. So let us understand the problem description first. We are given the root node of a binary search tree and a node, and we want to insert this node in the binary search tree. So let us take an example to understand this problem more clearly. So let us say we are given the root node as node 30. Since this is a binary search tree, all the values present in the left subtree of 30 will be less than 30 and all the values present in the right subtree of 30 will be greater than 30. So let us say the left child of node 30 is node 20. Now similarly for node 20, all the values present in the left child of 20 will be less than 20 and all the values present in the right child of 20 will be greater than 20 but less than 30. Okay, so for 20 the left child is 10 and the right child is 25. Now for this node 30, the right child is, let's say, node 45. Now for node 45 again, all the values present in the left subtree will be less than 45 and all the values present in the right subtree will be greater than 45. So for 45, what will be the value? Let's say the left subtree is nothing but 35 and the right subtree is null. Now the given node, that is new node, is nothing but node 28. So where do we need to insert this node 28? So let us see where do we need to insert this node 28. So if we compare node 28 with node 30, we can clearly see that the value of node 28 is less than the value of node 30. That means this new node will be in the left subtree. So we reached at node 20. Now for node 20, again we compared these two values. So for node 20 and node 28, node 28 is greater. That means it will be in the right subtree of node 20. So we reached on node 25. So we started with node 30, then we went on node 20, and now we are at node 25. Now for node 25, we compare. Okay, node 25 is smaller than node 28. That means node 28 will be present in the right subtree, and as we can clearly see, there is no right subtree, so we'll simply put node 28 here, and that will be our new binary search tree after inserting this new node. So we observe one thing from here, that a new node will always be inserted at the leaf. So a new node will always be inserted at the leaf. So let us take one more example to understand this more clearly. Let us say we are given the root node as node 45. The left child of node 45 is, let's say, node 35. Now for node 35, the left child is, let's say, node 25 and the right child is node 40. Now for node 25, let us say the left child is node 15 and the right child is node 30. Okay. Now for node 40, the left and the right child is null. For node 45, the right child is node 70. So let us say we want to insert node 38 here. We want to insert node 38 in this binary search tree. So how can we do that? So first of all, what we need to do, we need to compare this node 38 value with the root node. So let us compare it. So for node 45 and node 38, we can see that node 45 is greater than node 38. That means this 38, that means this new node will be present in the left subtree because it is smaller. So we reached at node 35. Now for node 35, we compare node 35 and node 38. So for node 35 and node 38, node 35 is less than node 38. That means node 38 will be present in the right subtree. So we reached at node 40. Okay, now for node 40, we check, okay, node 40 and node 38. Node 40 is greater than node 38. That means node 38 will be present in the left subtree. And now the next is a leaf node. So node 38 will be inserted here. So this will be our binary search tree after modification. I hope the problem statement is clear. I also explained you the solution approach meanwhile, but now I will explain you the solution approach in depth. So let us take an example to understand the solution approach. So let us say we are given the root node of the binary tree as 75. The left child of this binary tree is, let's say, 65. Is 65. Now the left child of 65 is, let's say, 55, and the right child is node 70. Now for node 70, let us say the left child is node 68 and the right child is node 72. Okay, fine. Now for node 75, the left child was node 65. Let us say the right child is node 88. Okay, now we want to insert a node 74 here in this binary search tree. So how can we do that? So what we need to do, we are going to start comparing this new node with the root node. So first of all, we will compare the new node with the root node. So for node 75 and node 74, node 75 is greater. That means this new node will be present in the left subtree, because all the values less than the current node will lie in the left subtree of that current node. So node 74 will lie in the left subtree of node 75. So we reached at node 65 now. Now for node 65 and node 64, node 65 is less than node 74. That means node 74 will lie in the right subtree of node 65, because all the values greater than node 65 will lie in the right subtree. So we reached at node 70 now. Okay, now for node 70 and node 74, node 70 is less than node 74. That means this node 74 will lie in the right subtree of node 70, because all the values greater than node 70 will lie in the right subtree of it. So we reached at node 72. Now for node 72 and node 74, node 72 is less than node 74. That means this node 74 will lie in the right subtree of node 72. Since there is no right subtree, that means we are going to put this node 74 here. Okay, and that's it. And now if we check, our binary search tree that was previously there is still a binary search tree. Okay, talking about the time complexity of this approach, as we can clearly see, we have made log of n operations or log of n searches. So the time complexity is big O of log n, where n is the number of nodes present in the binary tree. And talking about the space complexity of the code, the space complexity of this approach will be big O of log n if we are going to use recursion, and if we are going to use simple iteration, then the space complexity will be big O of 1. Now these time complexities and the space complexities are for average cases. Okay, but what will happen for the worst case? So let me take an example for the worst case as well. So let us say we are given the root node of the binary search tree as node 55. Now the left child of this node 55 is null and the right child is node 65. Now for node 65, the left child is null and the right child is node 75. Now for node 75, the left child is null and the right child is node 85. Now for node 85, the left child is null and the right child is node 95. Now if we want to insert a node, let's say 105 in this binary search tree, so what is the first thing? First thing, we are going to compare the root node value with this new node value. So 55 and 105. So 55 is less than 105. That means this new node will lie in the right subtree. So we'll reach at node 65. Now for node 65 and node 105, node 65 is less than node 105. That means node 105 will lie in the right subtree of node 65. So we reach at node 75. Now for node 75 and node 105, we again see, okay, node 75 is less than node 105. That means this node 105 will lie in the right subtree of node 75. So we will reach at node 85. Now for node 85 and node 105, 85 is less than 105, we again see, okay, so 105 will lie in the right subtree of 85. So we reached at 95 now. Now for 95, we can clearly see 95 is less than 105. That means this 105 will be present in the right subtree of 95. So 105 will be inserted here. And as you can clearly see, in this case we are making n searches, so the time complexity for the worst case will be big O of n. And what will be the worst case? The worst case is when our tree is given in the form of a degenerate or a pathological tree. I have already explained you in my binary tree theory part that what is a degenerate or a pathological series or a pathological tree. It is nothing but a binary tree in which every node is having only one children. Okay, and talking about the space complexity of this approach will be big O of n if we are going to use recursion, else big O of 1 if we are going to use iteration. I hope the average case and the worst case is clear to you guys. Now we are going to code our approach. So in this video I am going to cover the recursive approach, and I want you guys to do the iterative approach by yourself. I will drop the iterative approach in the comment section, but I will recommend you guys to please check it by yourself. Okay, so let's do the code now. So as you can clearly see, I have already declared a function called insert that is taking the root node and a new node as an argument. Now what is this root and new node? Root and new node are nothing but the objects of class tree node. This class tree node is having a constructor that is initializing the value of the node, the left child and the right child of a node by default set to as null. Now what was the first thing? The first thing that we need to do is, if the node that I'm currently on is a null node, so in that case we know that we are going to return this new node because we want to put this node at that value. Any node will be inserted on the children of leaf node. Okay, so return this new node, right? So if my root is none, from here we are returning new node. Now what is the second thing? The second thing is, if my root dot value is greater than new node dot value, that means the value present at the node is greater than the value present at the new node. In that case, the new node will be present in the left subtree. So we are going to make a call to the left subtree. So root dot left is equal to insert root dot left and then new node. So what we are doing, we are just making a call for the left subtree. Now whenever the left subtree is going to return me an answer, I'm just storing that answer as on root dot left. Okay, now else, obviously the second case is if root dot value is less than new node dot value. In that case, call for the right subtree because this new node will be present in the right subtree. So insert root dot right and then new node, and then after this I just need to return root from here, and that's it. That's all about the code. So let us take a very small example to run this code. So let us say we are given the root node as node 35. The left child of this node is 25 and the right child of this node is 45. And let us say we want to insert a node 28 in this binary search tree. So we also need to write in order because we want to see the output. So let us quickly write what is the in order as well. I have already told you the Inorder Traversal in my previous videos, so do check it out. So def in order, if my root is none, so if my root is none, in that case return an empty list. Okay, after that make a call to its left, because firstly we'll make the call to the left subtree in order, and then the current. So current will be nothing but root dot value in the form of a list, because we are going to return a list from at any point, and then for the right subtree. So in order is equal to in order of root dot right, and then we just need to sum all these three lists. So return left answer plus current plus right answer, so it will get added, and that's it. So let us call this in order. Firstly we need to Firstly, we need to say root is equal to insert and then pass the root and new node. The new updated root node will be stored, so let's call it new root. Okay, so new root, and let us call in order now. So print in order and pass the new root. Let us check the output of our code. So the output of our code is coming out to be 25, 28, 35 and 45. So let's verify our output as well. So I have taken the binary tree as node 35 was the left child. No, sorry, node 35 was the root node, node 25 was the left child of 35 and node 45 was the right child. I wanted to insert node 28. So node 28, so how it will be inserted? First of all, we will compare node 28 and node 35. So node 35 is greater. That means node 28 will be present in the left subtree. So we reached at node 25. Now for node 25 and node 28, node 25 is smaller. That means 28 will be present in the right subtree. So 28 will be inserted here. Now let us find the in-order traversal quickly. So how can I do that? From here, left, there is no left. So first value is 25 and then we reach to 28. Second value is 28. Next value is this and then 35, and the next value is 45. So our in-order traversal is coming out to be 25, 28, 35 and 45, which is matching with our output. I hope the code made sense to you guys as well. Now I will be uploading more of these videos in the upcoming weeks, so keep following us. If you guys still have any queries regarding this problem, please drop your concern in the comment section and I will be more than happy to help you. Till then, keep smiling and keep coding. Thank you.